Lagrange's theorem, in the mathematics of group theory, states that for any finite group G, the order of every subgroup H of G divides the order of G. The theorem is named after Joseph-Louis Lagrange. Proof of Lagrange's theorem. This can be shown using the concept of left cosets of H and G. The left cosets are the equivalence classes of a certain equivalence relation on G and therefore form a partition of G. Specifically, X and Y in G are related if and only if there exists H in H such that X equals YH. If we can show that all cosets of H have the same number of elements, then each coset of H has precisely H elements. We are then done, since the order of H times the number of cosets is equal to the number of elements in G, thereby proving that the order of H divides the order of G. Now, if R and BH are two left cosets of H, we can define a map F RBH by setting F equals bar minus 1x. This map is bijective because its inverse is given by this. Proof also shows that the quotient of the orders G, H is equal to the index G, H. If we allow G and H to be infinite, and right, this statement is then seen as a statement about cardinal numbers. It is equivalent to the axiom of choice. Applications. A consequence of the theorem is that the order of any element or of a finite group divides the order of that group. Since the order of A is equal to the order of the cyclic subgroup generated by A, if the group has n elements, it follows this can be used to prove Fermat's little theorem and its generalization, Euler's theorem. These special cases were known long before the general theorem was proved. The theorem also shows that any group of prime order is cyclic and simple. This in turn can be used to prove Wilson's theorem, that if P is prime then P is a factor of. Lagrange's theorem can also be used to show that there are infinitely many primes. If there was a largest prime P, then a prime divisor Q of the Mersenne number would be such that the order of P in the multiplicative group would divide the order of this group, which is hence contradicting the assumption that P is the largest prime. Existence of subgroups of given order. Lagrange's theorem raises the converse question as to whether every divisor of the order of a group is the order of some subgroup. This does not hold in general. Given a finite group G and the divisor D of G, there does not necessarily exist a subgroup of G with order D. The smallest example is the alternating group G equals A4, which has 12 elements but no subgroup of order 6. A CLT group is a finite group with the property that for every divisor of the order of the group, there is a subgroup of that order. It is known that a CLT group must be solvable and that every supersolvable group is a CLT group. However, there exist solvable groups that are not CLT and CLT groups that are not supersolvable. There are partial converses to Lagrange's theorem. For general groups, Cauchy's theorem guarantees the existence of an element, and hence of a cyclic subgroup, of order any prime dividing the group order. Solo's theorem extends this to the existence of a subgroup of order equal to the maximal power of any prime dividing the group order. For solvable groups, Hull's theorems assert the existence of a subgroup of order equal to any unitary divisor of the group order. History. Lagrange did not prove Lagrange's theorem in its general form. He stated, in his article Réflexions sur la résolution algébrique des équations, that if a polynomial in n variables has its variables permuted in all n ways, the number of different polynomials that are obtained is always a factor of n. The number of such polynomials is the index in the symmetric group Sn of the subgroup H of permutations that preserve the polynomial. So the size of H divides n. With the later development of abstract groups, this result of Lagrange on polynomials was recognized to extend to the general theorem about finite groups which now bears his name. In his Disquisitiones Arithmetici in 1801, Carl Friedrich Gauss proved Lagrange's theorem for the special case of Z*.
the multiplicative group of non-zero integers modulo p, where p is a prime. In 1844, Augustin Louis Cauchy proved Lagrange's theorem for the symmetric group Sn. Camille Jordan finally proved Lagrange's theorem for the case of any permutation group in 1861.